What is up, athletes? So let's look at proportion testing, proportion confidence intervals. All right. So let me give you the down low. And this is week 9 in our semester. How are you feeling? Because our numbers were a little down in the tutorial center yesterday. And so I'm trying to see, was it just an off day? Or are people feeling the fatigue? Because it is a long semester, right? Spring break's coming up. So I'm just curious, how are you feeling? How are you doing? Um, and just checking in. So comment down below if you will. I'm curious. All right. So what we're looking at, and we talked about this in class, and if you're not in my class, you might want to take some additional notes here because I'm going to give you some golden nuggets to look at, to think about. So look at this question. Working at home, according to the US Census Bureau, 36% of men who worked at home were college graduates. All right. So in a sample of 492 women who worked at home, 161 were college graduates. All right. So let's see what the question is. So the question is this: find the point estimate for the proportion of college graduates among women who worked at home. And then we're going to round to 3 decimal places. All right. So whenever, go ahead and underline or write down that word point estimate. So when we do this survey here, this is, out of this group, what percent of them worked at home? That's going to be like our best guess. And we don't have everybody's information. So this is the population. We're trying to get information about the population, but we're not going to go and ask everyone. It's going to be impossible. So we take a sample, right? A simple random sample. And we ask these 161 folks. Or sorry, we asked these 492 women, how many of you guys were college graduates? And 161 said yes. So this is like our best guess so that we could kind of get an idea of what the population proportion would be, right? So what we do is we take our X value, the people that said yes, 161, and we divide it by the total. And so this is called our sample proportion, also known as our point estimate. All right. And we label that, you see down here, as P hat. And so if you're ever trying to find P hat, all you do is do X divided by N, just like we did. All right. So here's 161 divided by 492, and there's our point estimate. All right. So next question. Now getting to the moneymaker. Construct a 98% confidence interval, right? If we do this 100 times, we're confident that 98 of those times, this interval that we come up with, the true population proportion will fall in between these two numbers that we get. All right. So we're going to construct a 98% confidence interval for the proportion of women who work at home who are college graduates. All right. So notice we're talking about percentages, and we're looking to construct a confidence interval for proportions. So underline proportions, and then also know, what are we trying to do? Underline, we're trying to construct a confidence interval. So you always have to understand there's a lot of programs that we have. When do I use each program? All right, because those programs are garbage if you don't know when and how to use them. They're super helpful when you know how to use them properly. All right, so let's get some numbers down that we're going to need. So notice we're constructing 98% confidence interval. So we have to make sure, all these conditions are met. So it's a simple random sample. The population is at least 20 times as large as the sample. The items in the population are divided into 2 categories, right? Those who were college graduates, those who are not. Let's see, the sample must contain at least 10 individuals in each category. So notice, if we had 162 that were women who worked at home, that means I'll do the total of 492 minus the 161, and that'll be 331 that fall in the other group. All right, both of those, the 161 and the 331, they're both at least 10. All right, so all those conditions are met. So now we could go ahead and run this helpful program. So we're going to use our TI-84 plus calculator. And I'm going to use the app, but it's going to be the same thing. So notice what it's going to ask of you. So when I load it up, when I use one prop Z int, so this is what gives me the confidence interval. What I'm going to need is I'm going to need an X value, I'm going to need an N value, and then I'm going to need the confidence interval. So going back to the problem, our confidence interval is 98%. So I'm going to put 0.98. Our N value was the total people sampled, the 492. And then our X value is how many said yes to whatever question I was interested in, 161. So let's go ahead and punch this in. So let me share my calculator. So we go second, vars, sorry, getting ahead of myself. I'm thinking of next week. Stat, test. So again, we do stat, and then go over to test, and then we're going to scroll down, and we're going to do one prop Z interval. Our X, what did we say our X was? I think it was 161. Our N, let me double check. I think it was 492. 492. And then we were 98% confident. We wanted to be 98% confident. Do 98. All right, let's calculate this bad boy. And so we get our lower and our upper. So the true population proportion, right, would fall somewhere in between here. So if we did this experiment 100 times using the same methodology, 98 out of those 100 times, boom, our true population proportion, whatever it may be, would be between these two numbers that we found. All right, so let's go back to the problem. And so as you see, that's how they get these two numbers. So we say we are 98% confident that the proportion of college graduates among women who work at home is between 0.278 and 0.376. All right, so we get an idea now of where the true average lies, right? So it narrowed our choice. So based on this confidence interval, is it reasonable to believe that the proportion of college graduates among women who work at home is the same as the proportion of college graduates, among men who work at home? All right, so if we look at the question, all right, let's go back to how this started. Notice how it started. It said 36% of men who worked at home were college graduates. So what we're going to do is we're going to take that 36%, oops, and we're going to see, is that 36, that 0.36, is it contained? Is it inside of our interval, right? And since it is inside of our interval, then we conclude that then the proportion of college graduates among women who work at home is the same as the proportion of college men. All right, so we're always going to compare that to the interval that we got. And again, this number we're trying to see, is it inside here for this particular question? All right, let's do another example, right? And they're all going to follow the same format. Let's see, let's look at number 3 here. All right. So in the sample of 43 water specimens taken from a construction site, 27 contained these bad levels of lead. All right, these contain detectable levels of lead. So here they want us to construct a 99.8% confidence interval for the proportion of water specimens that contain detectable levels of lead. So again, we're looking at, notice they don't tell us anywhere here that they don't give us any percentages, right? But what they do give us is they give us an X and they give us an N, all right? And they want us to construct a confidence interval. And you have to ask yourself, okay, what is this confidence interval for? Well, it's for a proportion, for the proportion, all right? So again, that's telling us to use one prop Z int. So there's our confidence level. This is our N, right? The sample size. And this is what we're looking for. We're counting how many of those specimens had detectable levels of lead. So 27. So this is our X. So let's plug this into our calculator. So let's go. Let me grab those numbers again real fast. X is 27, N is 43. So make sure you always label that so you know what you're plugging in. All right, so we're going to stat, test, one prop Z interval. And I always get these commercials. I don't know what that says. I think I picked the wrong one like I tend to do. I think I just signed up for some health insurance or something. Give me a second. Let me get out of here. All right, I gotta pick this one, I think. There we go, we're back. All right, so let's put these figures in. And I already forgot what these numbers are because of that commercial, the advertisement. All right, so let me grab these numbers real fast. Let me delete this. All right, so X is 27 and 43, 27, 43. And then our confidence level, 99.8.998. Calculate, and boom, there's our interval, 0.4001.8557 after I round. All right, so let's go back. And so what you're going to conclude, you'll go ahead and you'll put those numbers right there. So there's our numbers we came up with. And then we conclude we are 99.8% confident that the proportion of water specimens that contain detectable levels of lead is between boom and boom. So always make sure you restate, what is it that you found? What were you looking for? All right. So now they're going to want us to construct for part B 80% confidence intervals for that. All right. So again, the X stays the same. The N stays the same. The only thing you're changing is the confidence level. So now you're putting in 0.8. All right. And then you get these new levels. So notice when you decrease the percentage, the confidence level, right? This is our confidence level. When you decrease it, what happens is that your interval gets more narrow, right? So we get our interval becomes more narrow. Those two numbers become closer to one another. What is the effect of increasing the level of confidence on the width? So notice when you increase the level, so if I were to go from 80 to 99.8, right? So from here to here, there's an increase, right? From here to here. So notice these numbers get farther apart when you increase that percentage. So that becomes wider. The interval becomes wider. And that's what they want us to look at right there. All right, so that's what you're looking at. Just a short little video of how to use one prop Z int. All right, so if you have questions, you let me know. Actually, let me just make sure. I didn't miss any particular type of questions. Let's see, I think these are the same. These are the same, yes, yes, yes. And then let me just verify number 4 is the same because I don't want you guys. Oh, perfect. I'm glad I checked number 4. So for number 4, what do they? So they have an educator. They want to construct a 99.9% confidence interval for the proportion of elementary schools children in Colorado who are proficient in reading. All right. So the results of a recent statewide test suggest that the proportion is 0.71. Using this estimate, what sample size is needed so that the confidence interval will have a margin of error of 0.03? All right. So again, it's so important for you to identify what are they looking for. So here, for this question, they're not looking for a confidence interval. So it doesn't make any sense to use one prop zint because that's not what they're looking for. All right. What they're asking you is what sample size is needed. So write down this formula. So this is our formula for sample size. And you have two options here, all right? So when they don't give you a p hat, so we look here, do they give us a p hat? Boom, 0.71. So if a value for p hat is available, this is the formula we use. So for this question, we're using this top equation right here. If they don't give you a p hat, this bottom one is the equation you will use, okay? So you might ask yourself, well, where are they getting the 0.25? Well, what they're assuming is that the p hat is 0.5. So 0.5 and then 1 minus 0.5. So this is 0.5 times 0.5. That gives you 0.25. All right. So again, identify, do they give you p hat or not? So here they do. So we're going to use this formula. And you might ask yourself, well, how in the world am I going to get this Z right here? I notice a lot of people doing this the long way. That's absolutely fine to use this critical value here table. But again, I let you use your resource, which is your calculator. So what you're going to do is you're going to grab this 99.9% and you're going to plug that into inverse norm. So let me show you. And remember what we're going for, just so you can kind of get a sneak peek. We're going to try to get this value here for Z, or we are going to get this value of 3.291. And depending if you guys are using a table or not, this might be off slightly, right? Not by much. It's going to be almost the same number, but the table, right, and our calculators might give us a number that's a little bit different. If you want to see how to use the table, just comment down below. I'll be glad to walk you through it because I know not everyone's in my class. All right, so here we'll use inverse norm. Let's see the area we're going to plug in. So let me try something. So because I know a lot of people out there, they don't want to purchase this calculator, which is a lot of money, and you want to use this app. So the area, let me try this. Let me see if this gives me an option. I'm going to try putting 0.997. Is that the number, 0.997 that they gave us? 0.999, sorry. 0.999. And then the mean, we'll put 0, and then the standard deviation is 1, because we're looking at a standard normal distribution. And then let me see if I get this option. So I'm gonna hit second catalog, and let me see if it gives me a center option on this. So this doesn't actually. On some of your calculators, they give you an option where it allows you to pick right tail, left tail. Let me just go to the bottom to see if the programmer of this calculator gave us that option. Oh, that's too bad. Let me see if I go to math, second test. I'm just trying to do a workaround for people who don't have this. All right. So unfortunately, I'm gonna have to do this the longer way. So I'm gonna have to put in the area of the left tail. So the area of the left tail, what you're gonna do is, and I could draw this out for you real fast. Let me draw this out just so you can see what I'm doing. So notice, we have a standard normal curve, our mean of 0 is in the middle. Then we have this area, the middle area of 99.9%. So if this is 0.999, right? And this entire area under the curve is 1, right? So that means that these remaining tails, each of them would be whatever's left over. So 1 minus 0.999. Well, that would represent what's left over in both of these, the combined sum. But there's 2 tails, so that's why we divide by 2. And so when you see Z and then this little guy, alpha divided by 2, alpha represents the area in these tails, the total area. I shouldn't have done that. And the reason we divided by 2 is because there's 2 tails. All right, so this is what I'm going to punch in. This right here, I'm going to punch that in right here, just so you understand what I'm doing. But again, the vast majority of you that are in my class, you just pick center and it's so much easier. And that's why I would plead with people to please go to the library and get your free calculator. So you won't have to worry about all that. All right. So let's change this to, let's see, is it allowing me? All right, cool. 1 minus 0.999, and I'm going to take that quantity and I'm going to divide it by 2. Again, it's harder on mine compared to yours. And let's calculate that now. So what I just did is I found the area of the left tail. And so I get negative 3.2905. So if we go back, we get negative, or we get positive 3.2905. If we round to 0, we get 1. All right. And you might be wondering, why is this positive and we got a negative? Well, remember, in this formula, you're going to square it, so it doesn't matter. And if I want the right tail, then I just take off the negative and make it positive. All right. And we've discussed that in the past as well. All right. So now it's just a matter of plugging all these numbers in. So for those of you taking notes, let's rewind a little bit. Your first step was to find this z-score. How do you do that? Inverse norm. All right. Mostly everyone has the nice calculator, so you don't have to worry about all that stuff that I just did. It's just real straightforward. All right. So 0.71, that's our p hat, 1 minus 0.71. The z, we found it to be 3.291. Boom. M is 0.03, and that's right there. And then we square it. All right. So we get approximately, boom, this number right here. Any decimal you get, you're going to round this number up. So you always round up because we want to count. This is an n value, sample size, and we want it to be a whole number. All right. So we conclude that we need a sample of 2,478 elementary school children, all right, to obtain this. All right. Part B, they're just showing you, hey, what happens if you have no estimate of P, right? If you couldn't provide a point estimate, well, that's when we use this second formula, right? So we go with this second formula. And so it's just 0.25 times that the quantity of 3.291, that same z-score divided by m, margin of error, and you square it. And we get this when we round up. All right. So if an educator, this is part C, if an educator wanted to estimate the proportion in the entire United States rather than Colorado, would the necessary sample size be larger? Would the necessary size be larger? All right. So what's cool is that the size of the population does not affect this sample size, right? Because if you remember our criteria, we wanted if you looked at those 4 criteria, you wanted the sample to not actually be that big, right? And here, if we read their explanation, let's see, the size of the population does not affect the sample size necessary to estimate the proportion in the United States because the margin of error will be the same if the confidence intervals of the same level are constructed for both population proportions. All right, so therefore we conclude the necessary size would not be the same. And that kind of ties in to why you had those 4 criteria. All right, folks. So I hope you're having a great day. I hope this was helpful. I'll talk to you very soon.